Hi, Rachelle. All right, so we'll go through those questions that you had, and hopefully it'll help you out. I guess we'll see. So I'll start out with alcohols. So the alcohols have a similar naming process to alkanes, but there's a few kind of like additions or modifications. So essentially, we're going to say that we can divide the name up into a prefix, a root, and a suffix, right? So the prefix is going to be the part of the name that goes first, and it gives the position of any side groups or branches that are happening off the main chain. Oh shoot, you know what? I just had an example written out, and now I think I've misplaced it. I wonder if it was down here. Let me just have a look. Sorry. I got distracted as I was getting ready to make this video. Okay, maybe I don't have it now. Well, I think I can probably come up with the example on my own anyways. Okay, so the prefix is going to give the position of any side groups or branches off the main chain. Now the examples that I have down here don't have side branches, they're just straight alcohols, so I don't have that there, but I'll show you that in a second. Then you have the root. So the root is going to always be basically the root name of the parent chain, right? So whichever chain has the longest continuous chain of carbon. Sorry, this stupid headset keeps kicking off. Okay, I better make sure that it's still working. Oh yeah, okay. So the only thing is when you're figuring out which chain of carbons is the longest continuous chain, you need to make sure that it contains the hydroxyl group. And so like you were asking in the email, the hydroxyl group is this just OH together. Okay. Let me just double check if you asked other stuff about that. I'm understanding how to identify OH. Right. Okay. Um, and maybe I'll just answer that other question you had now too. So you're confused with what the functional groups are. So with alcohols, like you said, alcohols are a group of organic molecules that possess a hydroxyl functional group. So that, you're right, yes, that does mean that hydroxyls are the functional group, and any compound that has them is automatically an alcohol. So yeah, to answer your question, yes, every compound that possesses only a hydroxyl functional group will be an alcohol. I mean, there is a little bit of a variation on that, which is that, like, technically, you could have, um, you could technically have other functional groups on there and still have the alcohol group, but you don't need to worry about that for Science 30. So yeah, for your case, all you have to worry about is that if there's a what do you call it? Sorry. If there's a hydroxyl group, then you're looking at an alcohol. Okay, so the root name is going to be just based on like those meth, eth, prop, but kind of prefixes that I mentioned to you for how many carbons are in the parent chain. And then you're going to finish off the name with a suffix that has to end in OL because that indicates that it's an alcohol. So if you have like propane, for example, that ends in an E, you would drop the E and instead add OL. So it would be propanol, right? Now this one is a little bit different, so we'll get to that in a second, but propanol, right? The location of the hydroxyl group has to be indicated. So you basically have to have a number. So for example, here, if we have basically pentane, but it has an alcohol group on the second carbon in on one end of the chain, then you would say pentane, so the root name minus the E, always drop the E, pentane dash 2 to show that it's on the second carbon, dash OL to show that it's an alcohol. Okay, and I'll go through some more examples, so hopefully it'll make more sense to you. And then you also have to make sure that you're numbering your carbons from the end that's closest to the hydroxyl group. Okay. I'm pretty sure for you guys, you don't need to do it with more than one functional group, so maybe I won't worry too much about that. But I can quickly explain it to you. If you have more than one hydroxyl group, then you basically have to use multiple numbers to indicate where those hydroxyl groups would be. And if you have numbers between the name of the parent chain and the alcohol, component, then you don't have to drop the E, okay? Because we wouldn't want to have like pentan 2,3-diol. We want to have pentane 2,3-diol. So essentially what we have over here in these examples is neither one of them have side groups like a methyl group or an ethyl group or anything like that. So if we look at, for example, this structure, we have 2 carbons and each one of them have a hydroxyl group on them. So we would say, okay, the root name is meth eth, right? And then because we have more than one hydroxyl group, we have 2 hydroxyl groups, we're going to keep that E on the ethane, and then we're going to draw a dash. Now there's only 2 carbons here, so we don't have to worry about which way we number it. We would just say 1 and 2 are the locations of the alcohol groups or the hydroxyl groups. So 1, 2, and then to finish off, now this is where it gets a little bit tricky, and this is why I don't want you to stress out and memorize this, but basically because there's 2 alcohol groups, we use a different prefix. It's not like the meth eth that we use for the number of carbons. It's di, tri, tetra. So di would be for 2 alcohol groups, which is what we have here. So it would be di, and then we just finish off with the OL ending. Okay, so that one's like a little bit more complex than what you'll need to know. But you can probably see the general kind of an idea. Same thing here, right? We look at our parent chain of carbons. The longest chain of carbons is 3, so it's going to be propane. And then because it has 3 hydroxyl groups on it, there's going to be 1 on each carbon, so it's going to be propane 1, 2, 3. So those are each indicating each of the carbons that have a hydroxyl group on them. And then because there's 3 hydroxyl groups, we write dash tri to show 3 OL, 3 alcohols on there. Okay. Now what I did want to show you is, oh, that's what it was. I had it open in my book and then I was helping a student. Oh, shoot. Let me just quickly look up if I can find the alcohols in here really quickly. Not sure where I put those. Alkenes, alkynes. Shoot, I shouldn't have closed that all up. Oh, I wonder if I could use this. Oh, you do have diols in here. So actually, even in your textbook, you have ethane 1,2-diol. Now this is kind of weird because they do drop the E in here, which isn't usually the standard thing. So it says draw the chemical structure. So let's give that one a try maybe. So we have ethane 1,2-diol. You could always pause the video and see if you can do it now that I've explained it, and then I'll go through the answer. So we have ethane. So remember the prefix is telling us the parent chain. So we have meth eth, which is 2 carbons. And then we have 1, 2. So one alcohol, and di means there's 2 alcohol groups. So we know there's going to be OH on each one of those carbons. And then the rest is just going to be filled in with hydrogen, right? So it's going to be like this. And so that would be our result. Now the other thing you could have, if you had ethane, you could have 2, 2-diol. And all that would mean is that, let's say, or sorry, no, actually it would never be 2, 2. It would be 1, 1. Okay. So essentially what you would have is, because we always number from the carbon that has the hydroxyl group on it. So we would say like this is carbon 1, that's carbon 2. Carbon 1 would have 2 OH groups on it. Okay, so that's also a possibility. Let me think. I wish I still had that question that I was going to give you. I feel like it was, let's see, 3-methyl 3-methyl, what did I have? 3-methyl, oh, that's what it would be. 3-methyl prop and dash 1 all. Okay, So with this one, this is kind of what I was talking about here, where I said there's a prefix that gives the position of a side chain. So essentially what this is saying is I have, if I look here, this is going to be my prefix, this is going to be my root, and then this is going to be my suffix. So my root is telling me that I have propane, which is 3 carbons, right? And then what this is telling me is that on the 3rd carbon, I have a methyl group. So basically, it doesn't really matter which way you number it. I could go left to right, 1, 2, 3. So on this carbon, I'm going to have a methyl group, which is always just a carbon with 3 hydrogens, right? Meth is 1 carbon with 3 hydrogens around it. And then it says I have 1 all. So that means on the 1st carbon here, I have an alcohol group or a hydroxyl group. And then everything else will be filled in, right? Hydrogen, 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 like that. So that would be my structure for that one. Okay. I don't know. Hopefully that kind of makes sense. If it doesn't, let me know and I can do more alcohol examples for you. Let's see what else. Okay, so then the next thing you said you had a hard time with was the esters, I believe. Or sorry, no, carboxylic acids. Okay, so with carboxylic acids, because you were saying, sorry, I'm just trying to catch where you were at in here. Am I understanding that carbonyl? Oh, right. Okay, so you're looking at the difference between like carbonyl, carboxyl, and as in every carboxylic acids, the textbook says the carboxyl functional group contains 2 oxygen atoms joined by the same carbon atom. All carboxylic acids contain this combination of functional groups. So that, yeah, that means that carboxylic acids contain that functional group, which classifies them as a carboxylic acid. So the second part of what you said in the email there is correct. Okay, and so here we can see a carboxylic acid is an organic compound that contains a carboxyl group, which is the COOH group. And so that's going to be composed of a carbon double bonded to an oxygen, and that's called the carbonyl group. And then the carbon is also attached to a hydroxyl group. And together, these 2 different groups constitute a carboxyl group. Let's see, because the carboxyl group uses 3. Oh yeah, and that's another good thing to be aware of, is that because the carboxyl group uses 3 of the carbon's 4 bonds, it's always going to be at the end of a chain. So that makes it kind of nice and easy to locate. Yeah. So let's look at what the naming rules would be, because I think you mentioned that you didn't like that they don't do steps. The naming is basically the same as with an alcohol. So the prefix, again, is going to give the position and name of any groups that would be off the main chain. The root is where you count the longest continuous chain of carbons that include the carbon in the carboxyl group. Okay. The carbon in the carboxyl group always has to be numbered number 1. And then once you've named that, you can end it with -OIC acid. And again, just like we saw with the alcohols, if you have an E at the end of your parent name, like ane, then you want to drop the E and just add oic acid. So like, for example, we would have butane, but you see that they change it to butanoic acid, so the E is gone. Let's see, I just kind of made a side note here as well. COOH or HOOC can represent the carboxyl group when you see a condensed structural formula like we see here. And then if you were looking to name this one, you need to find your longest chain that includes this one. So if we start at this carbon, 1, 2, 3, 4, or 1, 2, 3, 4. And it doesn't actually end up mattering because either way, the thing that branches off is just going to be a methyl group. So let's say we go straight across. So we have 1, 2, 3, 4 carbons. And so that means our root name is butane. Okay. But then remember, our prefix has to give the position and name of any side chains. So if we start numbering our carbons here, we have carbon 1, 2, 3. So off of carbon 3, whether we go that way or that way, we have a methyl group. So we'd say 3 methyl. and then butane, and then we want to take the E off and end it in oic acid. Okay, so that's how we would name that one. I did put in another example here as well. Oh shoot, I meant to print it in color because I actually have it color coded. Oh well. Let's see. Basically all I would have had color coded would have been like the methyl groups are both the same color, the carboxyl group would be a different color, and the ethyl group would be a different color. So essentially if we look at this before you can see the whole name here, here's our carboxyl group. So we always want to number that one carbon number 1. And then from there, we want to figure out what the longest chain would be. So if we go 1, 2, 3, 4, obviously not the longest. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, if we go either way, right? So it doesn't really matter which one we pick there. I usually just pick the straight chain if I'm numbering, and it doesn't matter. So our parent chain has 6 carbons, so we know we're looking at hexane. Okay, so if you wanted, you could always start writing that down like hexane, dropping the E, of course. And then I would look at numbering. Now, the tricky thing if you're numbering side groups, and I'm not sure if you need to do this one either, but the tricky thing with naming side groups is you would need to make sure that you number them so that they're in order alphabetically. So basically, if we have number 2 here, carbon number 2 here has an ethyl group on it. Ethyl is lower alphabetically than methyl, so you want to make sure that you name that one first. So if we're doing our prefix, we'd say we have 2. I have to think about whether I do commas or dashes. It's been a little while since I did this. Okay, so it would be 2 ethyl, and then 4, 5. So I'd do 4, 5 because these are the same groups. So 4, 5 dimethyl. So that's the tricky part, is you always have to make sure if there's more than one of the same groups, you give their positions separated by a comma, and then you also have to make sure you include that prefix to say how many of them there are. So di, and then the name of the group. So dimethyl hexane. So now we've done everything that's on there that's different. So now we just have to finish off the name to show that it's a carboxylic acid. So dimethyl hexanoic acid. Okay. And so yeah, you can see that here. And I also mentioned that there's alphabetically lower branch has to be named first. Okay. I also gave an example here of drawing. So maybe I'll just see if I can put this down. So draw and name 2 different carboxylic acids that have the molecular formula C4H8O2. This one is, again, a bit of a challenge question, but essentially you have 4 carbons. So let's just go with whatever is easy. We have 8 hydrogens. Now remember, with the carboxylic acid, we have to have an OH group, so that's going to account for one of them. And then we have to have the double bonded oxygen. Okay, so that's our 2 oxygens right there. We have 1 hydrogen, so we have 7 hydrogens left to go. So we can do 1, 2, 3, 4, 5, 6, 7. And that would make sense because this carbon has 4 bond spots filled. So now we could basically say, I mean, this would be the easiest possible one, right? Because you have carbon 1, 2, 3, 4. So it's going to be butanoic acid. And there's no side group, so you don't need to include anything off of there. So that would be the simple one. I did show how you could do one that's a little bit more complex, where you have a parent chain that's like 3 long, and then you have a methyl group off of it, which should end up with the same number of carbons and hydrogens. And so with that carbon methyl group off there, we would number it, because it's going to be, this has to be carbon number 1, so carbon number 2 has a methyl group on it. And then the rest of it is going to be, now we only have 3 carbons on the parent chain, so it's going to be propane, and then the ending oic acid. Okay. Oh my goodness, hopefully this isn't going on so long that you're so bored by now. Let's see. Okay, esters is the last one that you asked me about, and I think I've answered all your question with the carboxylic acids. Clarify the functional groups / the names, carboxylic acids, and the differences. I'm just trying to think. I think I answered that. Clarifying the names, the functional groups, and the differences. Yeah, the only thing that I would say is like that maybe I haven't specifically pointed out yet is like with an alcohol, for you, it should only ever have this alcohol group on it, an OH. So if there's ever an OH and a double bonded oxygen like this, then you know it has to be a carboxylic acid, because you guys in Science 30, you don't need to know something that would have two different functional groups on it. So basically, if you see this functional group, the carboxyl, with all of those components joined together exactly like that, then you know that it's a carboxylic acid. Okay, let me see, you had a page number 268. 268. I could kind of look at some of these problems for you a quick second. They give you something there. So propanoic acid, if you use the systematic name to draw the chemical structure. So yeah, again, you would just say, what is the root? Well, it's propane, so I know I need to have 3 carbons. And then I have the suffix oic acid, so that means that it has to have one of those 3 carbons, has to include the C double bonded OH, right? So propanoic would be 1, 2, 3, propane. And the first carbon, well, it doesn't matter which one, but has to have an oxygen and a hydroxide group on it. Once you have that done, you would just fill in your hydrogens around the rest of it. So you would say, okay, I don't know if they were asking for the formula or the drawing, but this would be your drawing. And then you could always write it as a formula, because you would have C3, H, 1, 2, 3, 4, 5, 6, 7, O2. Right? Or, I mean, the more common way to write that would actually be C3H, or no, C2H5COOH, C2H5COOH. And the reason why we normally write that is because our name, like our structural or our condensed formula, is actually showing the structure of the compound, right? Where we have 2 carbons that are only singly bonded to hydrogen, and then we have the carbon that has the hydroxyl group on it. Sorry, it should be actually be C2H6, because I forgot about the hydrogen that's on this carbon. Yeah, I don't know. Hopefully that makes sense to you. Let me know if, I don't know, if you need more clarification. Let's look at esters really quickly before I wrap it up. So esters are, yeah, definitely the trickiest ones, like I think you probably kind of indicated in your email. So esters are hydrocarbon derivatives that contain an alkylated hydroxyl group. And so basically what that is, an alkylated hydroxyl group contains a carbon that is double bonded to an oxygen, has a single bond with another oxygen, and then has a single bond to what we call a variable group. So this could either be a hydrocarbon or a hydrogen. Okay, so off of this carbon with the double bond, you can either have this R1 basically, can either be H, or it can be any number of other carbons. So let's say carbon X with any other number of hydrogens. Okay. And then on the other side of this single bonded O, this same thing, this variable group has, oh, actually, I guess it's not the same thing. And actually, I didn't see that I had that written down there. So R1 has the hydrogen or hydrocarbon. R2 has to be a hydrocarbon, okay? Because if this was oh yeah, that's right. Because if that was a hydrogen, then as you can see, this would be a carboxylic acid, right? Because you'd have the double bonded O and then the OH. So this one can't be an H. It has to be carbon and then whatever else. So again, CXHY could be any number of carbons and any number of hydrogens attached to it. You don't need to worry about solubility, so I wouldn't worry about that. So the naming rules for this, again, as with all of the organic compound names, we have prefix, root, and suffix. So in the prefix, you count the number of carbon atoms in the chain that are attached to the oxygen in the alcohol part, right? So this singly bonded oxygen. So if you think about if on the other side of it, if we have a hydrogen, that would make it an alcohol. So, but instead, because there's never going to be a hydrogen here for an ester, we count the number of carbons that are over on this side of the oxygen. Okay, so you just have to be really careful about figuring out, and that's maybe a good way to think of it is think of like, if this was a carboxylic acid, where would the hydrogen be? Well, it would be on this oxygen, right? It'd be OH. So instead of the H group there, how many carbons are there? And that's going to be your prefix as that alkyl group. And then you need to add a space before you write the next part, right? So like you've seen probably with the names, it's going to be like the name of that chain, space, and then the name of the second component over here. So in this particular case, we have an oxygen single bonded to a single carbon, and so that's going to be a methyl group, right? So we have methyl space, and then the root name over here is going to be the longest carbon chain that includes the carbon that has the double bond on it. So basically you would go, okay, I have one carbon that's double bonded to the oxygen and then another carbon. So that's two, so meth eth. So ethane is going to be my parent chain here. And it'll include any side groups, but I'm pretty sure for Science 30 you don't need to know any side groups off of this chain. So all you would have to worry about is the ethane part. And then for the end of it, essentially just the way we did with ethanoic acid, instead of oic acid, you're substituting in O8. So remove oic acid from the name of the parent acid and replace it with O8. Okay. So parent acid, all that means is like if this oxygen would have had the hydrogen, then we know that its name would have been ethanoic acid, right? And so when we name an ester, we just replace the oic acid with O8. Yeah, hopefully that makes sense. I'll go through a couple of examples to see if it kind of helps you. Let's see, what do we have here? So for this one, I guess I'll just walk you through it instead of trying to draw it all out. We have, this is kind of our structure here, right? So we have a carbon double bonded to an oxygen, and then it's singly bonded to another oxygen. And that oxygen, remember, if it would have had a hydrogen here, that would have been methanoic acid because you would have had one carbon and then an oxygen with a hydrogen. But because we've replaced that hydrogen with this group of hydrocarbons, we first of all want to name that component here. So meth, eth, prop is how many we have off of the alcohol side. So we call it propyl. And then we put in a space, and then looking over on this side, it's really easy because we only have the carbon that's attached double bonded to the oxygen. So that would be meth. And then instead of methanoic acid, we say methanoate. Okay. Let's see. This one's a little bit trickier because I don't think you guys do line diagrams in Science 30 at all. But essentially what it is like each spot, like each end of a line is a carbon. So in this one you would look and say, okay, here's a carbon that's double bonded to an oxygen. And then it's singly bonded to this oxygen, and that oxygen has one carbon group off the end. So basically what would be at the end of this chain is CH3. And so we call that methyl, right, because it's on the alcohol side. And then we leave a space, and then we would figure out this side. So if we count starting at the carbon that's doubly bonded to the oxygen, we'd say 1, 2, 3, 4, 5 is our longest chain. So that means we have pentane, right? Now this one does show you what you would do if you have a side branch, which would be you always start numbering from the double bond. So 1, 2. Off of carbon number 2, we have a group of carbons that are one carbon, two carbons. So it's going to be an ethyl group. So now we would do 2-ethyl and then just continue the name on. It would be pentanoic acid, but because it's combined with that other group there, we call it pentanoate. Okay. Last one that I have here. This is all from my Chem 30. I'll also attach these notes to your to the email, because I can't remember if I sent them to you or not. So I'll attach it to your email and you can see if it helps you out at all. What is the name of the compound? CH3, CH2, CH2, COO, CH3. Okay. So if we think about what would be going on there, I find sometimes it helps me to draw it out. So I'm going to have CH3, CH2, CH2, and then COO. So that means I'm going to have the double bonded O and then the single bonded O. And then on the other side of that single bonded O, I'm going to have a CH3. Right, so now I can see a little bit easier how to name this. So I want to start with the one that's on the alcohol side. So instead of a hydrogen here, I have a methyl group. So it's going to be methyl. And then looking over here, I have meth, eth, prop, bute. So methyl butane. Drop the E and add O8 instead. So it's going to be methyl butanoate, which would be B. Okay. Let me just see here what you all said about the esters. Totally lost on this one. Do all esters have a carboxylic C double bond O OH and a separate? Oh, yeah, so hopefully you got that already, but basically no, with the esters you don't have the OH. So that's what makes it different from the carboxylic acid. I can have a quick look at the ones you mentioned, page 272, see if there's maybe a sample problem we can look at in here as well. Oh, and actually this one is showing you the reaction that joins them, right? So you have an alcohol and an ethanoic acid, and that's why we have both of those kind of components. Let's have a look at this practice problem here. So the ester depicted here produces an aroma similar. Oh yeah, that's another thing. Esters are usually responsible for like fruity type scents and flavors. Write the systematic name for this ester. Okay, so again, if we look here, we have the carbon double bonded to an oxygen, and it's okay for that carbon to have a hydrogen, but when it singly bonds to the oxygen on the other side, we need to have a functional group that is made up out of multiple carbons, or actually it doesn't have to be multiple, one or more carbons. And so here we would look on the left side here, we have 1, 2 carbons, so that's going to be meth, ethyl. Okay, and then going up here we have just the one carbon attached to the doubly bonded oxygen, so that's going to be meth. And then we want to, instead of oic acid, we want to do methanoate. Okay. Let's see. I could always go through, see if there's any practice ones. Benzocaine is an organic compound that's able to dull the sensation of pain, blah, blah, blah. Copy this structure and draw a box around the ester functional group. So if you might have, maybe you should just like pause and try and do these, but otherwise you can keep on watching. So that functional ester group that you should have picked would have been basically like, well, this is kind of like the R group, so I guess it'd be like C double bonded O and single bonded O, although technically that'd be a part of it as well. But I don't know, it's kind of weird because what would they actually qualify as the, it's the COO, but it should be the R. I don't know, like personally, this is what I would say as the functional, whoops, this is what I would say as the functional group, right? You have an R value off of here, like a variable group and a variable group. I guess you would probably say just like this component here, the C double bonded O and single bonded O. You won't have to do that in a test though, you just have to recognize that the functional group is there and know that it belongs to an ester. Circle and label the part of benzocaine molecule that is derived from an alcohol and the part that is derived from a carboxylic acid. So basically, excuse me, so basically the alcohol part is going to be these two carbons together with this oxygen, which would have normally had a hydrogen off of it to make an alcohol, right? So you could circle that part. I don't know if that's visible with my giant hands in the way. Yeah, so like that. It's hard for me to see what I'm doing on the screen and up there. Okay, and then the carboxylic acid part, of course, is going to be the C double bonded O, and then everything else here. Okay. Let's see. State the name of the alcohol used in the production of benzocaine. So ethanol. Okay. State the name of the alcohol. We just did that. Explain why people who have allergies to sunscreens containing PABA may also. I don't really know. I'm not sure what PABA is. They probably mentioned it somewhere in the textbook, so you probably know that one. I'm assuming that it would be because they probably have similar functional groups. Draw the structural diagrams for the products of the following reactions. Where possible, write the names of the chemicals, substances involved. Okay, so basically with this one, you would just want to look at, let's see, you have an alcohol here. So, and then you have your carboxylic acid here. So remember, basically, the hydrogen from here is going to combine with the hydroxyl group here. And so you should have CH3 is going to be joined to, I'm going to work kind of backwards here. And sorry, I'm actually way out of the screen. So I would do this CH3 here, which is bonded to the oxygen. And this hydrogen is going to join with this hydroxide to leave the group. So now instead, this CH3 will be bonded to an oxygen. And on the other side of that oxygen, we're going to have this stuff going on. So the C double bonded oxygen. And then combined with, let's see, your benzene group with the OH off of it. Oh, and that's an example of what I was talking about earlier, where you can technically have more than one functional group, right? So we can have the alcohol on there as well. However, just because this is on this group doesn't make it an alcohol necessarily, right? It's just that the functional group can be present on other substances. In Science 30, you would never be asked to determine whether, let me think about that. You shouldn't be asked to determine whether this is an alcohol or an ester with that functional group on there. I would say not. Okay, let's see, what else do we have? We have CH3, CH2OH, CH3, CH2, and then that's bonded to an OH, which is the alcohol. And then we have an HCOOH, right? So that's going to be like CH double bonded OH. So essentially this is our acid component. This is our alcohol. So remember what you always want to have happening here. This hydrogen that was on there is going to combine with these two and kind of go away. So now this oxygen is going to be directly linked to this carbon, which has a double bonded oxygen and a hydrogen on it. And so now if we wanted to name this, we could say, first name your alcohol group, methyl. And then we only have one carbon here, so methanoate. Okay. Last one, ethanol and ethanoic acid. So ethanol is going to be CH3, CH3, CH2, 3, 1, 2, 3, yep, CH2OH. And then ethanoic acid is going to be, so plus CH3, C double bonded O bonded to an OH. So again, we need to combine these two together. So this hydrogen is going to join up with this hydroxide group to form water. And so we're going to have CH3, CH2, and then single bonded to an oxygen, single bonded to this carbon on this side, double bonded to an oxygen, bonded to a CH3. So there's our product, and so we would call this methyl ethanoate, right? Because you have 2 carbons there as well. All right, well that was super, super long. So hopefully it helps you. I feel like maybe I was kind of blabbering a little bit, but yeah, hopefully it helps you out, and let me know if anything is still unclear and I will make another recording for you. Actually, sorry, just before I wrap up, I'm going to make sure if you could help explain the naming concepts with some examples. Right, okay. Well, hopefully I did that. And hopefully it made somewhat sense. Yeah, okay. Let me know if you need help with anything else. Thanks. Bye.